This is our velocity control of a DC electric brush motor circuit created for electronics and instrumentation, EN 530.241, spring 2010. Alright, this setup here creates a constant 2.5 output voltage up top and a negative 2.5 at the bottom. And depending on how we turn the potentiometer, it can exhibit either a 2.5, anywhere between a 2.5 or a negative 2.5 voltage. This principle is demonstrated on the circuit board. As you can see, the potentiometer is turned completely clockwise right now, meaning it's at a positive 2.5 volts DC, as you can see on the DMM here. As I turn the potentiometer counterclockwise, the voltage is going down, and thus the motor is slowing down till I reach the dead center of the potentiometer turn, and basically I'm reaching zero. If I continue all the way counterclockwise, I reach a final voltage of negative 2.5, which is exactly what we want.
So from the potentiometer we get our output, which is between 2.5 and negative 2.5 volts. And we feed that into the instrumentation amplifier, which is INA 111, and the INA 111 has a gain of 3.56, and in order to maintain that gain, we calculated that the resistance had to be 19.32 kilo ohms, which you can see here these two resistors have a combined value of 19.32 k ohms, and then the output from the instrumentation amplifier goes into the current amplifier, which feeds current into the motor and drives the motor. So the motor has a tachometer on it, which measures the angular velocity and outputs a certain voltage. We get that voltage from here. The tachometer voltage gets fed into the comparator we have here. And what the comparator does is it compares the tachometer voltage to 0 volts. And when the tachometer voltage is positive, it means that the motor is going clockwise. And when it's negative, it means that the motor shaft is turning counterclockwise. And we have a quality control circuit which checks if the motor is turning to right or left. And when our voltage output from the potentiometer is 2.5 volts, or when it's above 0 volts, we light a green LED, meaning that the motor is turning right. And if I turn the potentiometer all the way to the left, you can see that the red LED lights up because the motor is going in the counterclockwise direction. Another quality control circuit we have is the circuit that checks if the motor shaft velocity is within 10% of what we desire it to be. And how the circuit works is a little complicated, so we are going to show it on the schematics here. So we have another INA 111 instrumentation amplifier here, which has a gain of 1, and we maintain that by not connecting any wires between the two RG terminals. And what this INA 111 does is it gives us the difference between VTAC and VCommand, and that gets fed into an absolute value circuit, which always outputs a positive voltage. The other circuit is we have a voltage divider here, which takes the 10% of VCommand and feeds it into another absolute value circuit. And the outputs from those two absolute value circuits get fed into another comparator, and the comparator compares these two voltages and sees if the 10% voltage is less than or greater than the delta V and if the voltage is if the 10% voltage is less than the delta V, we light a green LED, and otherwise we light a red LED. We can see this applied on the circuit in this region. These LEDs are indicating whether we have the quality control circuit working. So when the green LED is running, when the green LED is lit up, the motor is turning within the desired 10% velocity. And then if I hold it, you can see that the red LED lights up, meaning that we're going slower than the desired velocity.
Alright, this is the last part of our circuit. This is the extra credit current monitor portion. And what this essentially does is it takes the voltage from the 2 ohm resistor on the current amplifier and sends it into a unity gain. And the purpose of this unity gain amplifier is just to avoid making any alterations to the current going through the current amplifier. After going through this, it is sent into a similar absolute value circuit as we had in the previous diagram, which is then sent into the LM311 comparator. Essentially what this portion does is it compares a voltage of 0.5, which is obtained from this portion that we created down here, which is essentially a voltage divider. This signal right here is 2.5, and which is divided using a 4 kilo ohm resistor and a 1 kilo ohm resistor. From here, a 0.5 volt signal is sent up into the negative terminal of the comparator, and this is compared to the signal sent out of here. And the reason 0.5 is so important is because since it's a 0.25 amp limit that we're looking for, that would imply because of Ohm's law that a 0.5 volt limit is what we want, because of 0.25 times 2 equals 0.5. Now, from the collector, that signal is then sent into the same LED circuit that we have at the end, and basically if it's above 0.5, then the red LED will light up, and if it's below, meaning within the 0.25 amps that we're desiring, then the green LED will light up.
So the circuit we designed can be used in applications such as quality control in basically any device that's using a motor to drive a load. We think that this project was really fun and educational, and we thank our professor, Lisicom, and our TAs for the help and for this project, for the opportunity to apply what we learned in class and get a hands-on experience.